Hello, cosmic explorers. Welcome to a journey into one of the universe's most mind-bending phenomena, gravitational waves. For centuries, we've understood gravity as a force, an invisible hand pulling everything towards everything else. But the story is far more intricate, far more dramatic than that simple explanation suggests. Today, we're diving deep into the ripples in spacetime itself, the echoes of cataclysmic events billions of light-years away. Can you imagine the sheer scale of energy needed to create disturbances in the very fabric of reality? Imagine dropping a pebble into a still pond. You see ripples spreading outwards, right? Gravitational waves are similar, but instead of water, they're ripples in spacetime, the four-dimensional framework of our universe. These ripples are generated by some of the most violent and energetic events imaginable. We're talking about colliding black holes, merging neutron stars, and supernova explosions, cosmic events that release more energy in a fraction of a second than our sun will in its entire lifetime. But how do these incredibly powerful events create these ripples? Well, think of it this way. Massive objects warp spacetime around them. The more massive the object, the greater the warp. Now, imagine two incredibly massive objects orbiting each other at tremendous speeds. As they whirl around, their gravitational fields interact, creating these ripples that propagate outwards at the speed of light. These are the gravitational waves. For decades, the existence of gravitational waves remained a theoretical prediction, a beautiful mathematical consequence of Einstein's theory of general relativity. Einstein himself predicted them a century ago, but detecting them proved to be an immense technological challenge. Why? Because gravitational waves are incredibly faint. By the time they reach Earth, the stretching and squeezing of spacetime they cause is minuscule, a fraction of the size of a proton. But what if? What if we could build a detector sensitive enough to measure these infinitesimal changes? That's precisely what scientists did. They built laser interferometers, incredibly precise instruments that measure the distance between mirrors with astonishing accuracy. These detectors, like LIGO and Virgo, are essentially giant L-shaped structures with arms stretching for kilometers. A laser beam is split and sent down each arm, bouncing back and forth between mirrors. If a gravitational wave passes through, it stretches and compresses spacetime, causing a minuscule change in the distance the laser beams travel. This change, though incredibly small, is measurable, providing irrefutable evidence of a passing gravitational wave. The first direct detection of gravitational waves in 2015 was a monumental achievement, a triumph of human ingenuity and scientific perseverance. It confirmed Einstein's century-old prediction and opened a new window into the universe, a window that allows us to observe events that are invisible to traditional telescopes. Before this detection, our understanding of the universe was largely based on electromagnetic radiation, light, radio waves, X-rays, etc., but gravitational waves give us a completely different perspective, a way to hear the universe's most violent events. We can now listen to the death throes of black holes, the collision of neutron stars, the echoes of the Big Bang itself. This is a paradigm shift in astronomy, allowing us to study the universe in ways we never thought possible. Each detection reveals crucial information about the nature of these cataclysmic events, providing insights into the properties of black holes, neutron stars, and the very fabric of spacetime. But what exactly can we learn from these faint ripples in spacetime? Well, a lot. The data from gravitational wave detectors provides incredibly precise measurements of the masses and spins of black holes and neutron stars involved in these mergers. This allows scientists to test our understanding of gravity in extreme environments, pushing the boundaries of our current theoretical models. Furthermore, the detection of gravitational waves from neutron star mergers has provided direct evidence for the creation of heavy elements in the universe. The gold, platinum, and other heavy elements in our jewelry and technology were likely forged in these cosmic collisions. Can you imagine? The very atoms that make up your phone might have originated in a cataclysmic event billions of light-years away, an event we can now detect thanks to gravitational waves. The study of gravitational waves is still in its infancy, but the discoveries are already staggering. The more sensitive our detectors become, the more gravitational wave events we'll detect, and the more we'll learn about the universe's most powerful and mysterious processes. Future detectors, even more sensitive than LIGO and Virgo, are already under development, promising an even richer harvest of data and an even deeper understanding of the cosmos. These advanced detectors will allow us to probe the universe's earliest moments, potentially revealing secrets about the Big Bang itself. Imagine the possibilities. And this is just the beginning. The detection of gravitational waves has opened up a new era in astronomy, an era where we can listen to the universe's symphony of gravity. As technology improves and our detectors become even more sensitive, we can expect a flood of new discoveries, each one revealing more about the universe's hidden wonders. We're truly entering a golden age of gravitational wave astronomy, an age where the mysteries of the universe are gradually being unveiled, one ripple at a time. But the quest doesn't end there. Scientists are constantly working to improve the sensitivity of gravitational wave detectors, aiming to capture even fainter signals from more distant and less energetic events. They're also exploring new ways to detect gravitational waves, such as using space-based detectors. A space-based detector would be less susceptible to noise from seismic activity and other terrestrial disturbances, allowing for the detection of even weaker signals. These future advancements will undoubtedly lead to even more profound discoveries, revealing more about the universe's history and the nature of gravity itself. The study of gravitational waves is a testament to human curiosity and ingenuity. It's a reminder that even the most seemingly impossible challenges can be overcome with perseverance, creativity, and collaboration. The detection of these faint ripples in spacetime is not just a scientific achievement, it's a testament to our ability to unravel the universe's deepest secrets, to listen to the whispers of gravity itself, and to expand our understanding of the cosmos. So, next time you look up at the night sky, remember that you're not just seeing the light from distant stars and galaxies, you're also listening to the echoes of some of the universe's most dramatic events that have left their mark on the very fabric of spacetime. And that, my friends, is truly awe-inspiring.